In this video, we're continuing on with circle properties, looking at some more ideas, for instance, tangents, secants, and segments, as well as looking at some further theorems of circle geometry. So starting off, we have these four new ideas that we want to look at. We've got secant, tangent, segment, and then also this idea of being external to the circle. So external to the circle, secant, tangent, and segment. So external to the circle just means you're outside the circle. So check it out here. We've got point A, B, and E. All of those points are outside of the circle. If you're on the circle, you're not outside the circle. So this point D, even though it's on the tangent, is still considered in the circle. Secant is a line that cuts a circle at two distinct points. So we can see here AB cuts the circle at G and F, so it is a secant. A tangent is a line that touches a circle at one point. So this line here, EB, has a tangent at point D. And a segment is a region of a circle cut by a chord. So in this case, where we've got that chord GF, we've got a segment up there, and we've got a segment below as well. In this case here, we've got chord AB. It divides the circle into two segments. Angle BAT is the segment that is closest to tangent AT. Angle APB is said to be in the alternate segment to BAT. So if we've got one segment here, we've got the alternate segment over here. Let's actually do that in a different color. So we've got our alternate segment in the orange there. So, some useful theorems. Theorem number 8. A tangent and a radius intersect at right angles. So, if you take a line out from this center to the edge, that's of course going to make a radius. If you then draw a tangent at that point, it has to be at a 90-degree angle. So the symbol for that is just a circle with a tangential line and then a radius that is perpendicular. Two tangents drawn from an external point. So if we limit the point P, or not limit it, but rather if we sort of label that point, make it both coming from that single point, the two tangents are going to be congruent. So the distance it takes for me to get from P to the tangent A is the same as the distance that it takes to get from P to the tangent B. And we can see that there's only going to be two tangents that are possible to draw from this point, one at the top and one at the bottom. If I try to draw it anywhere along here, it's going to be too shallow of an angle. So this creates an isosceles triangle there between the chord AB. So the symbol for that is just a circle with two lines coming out, almost like a bird's beak. And then we just write two lines to show that those two lines are the same. Okay, theorem 10. The angle formed by two tangents meeting an external point is bisected by a straight line joining the center of the circle to that external point. So if we got our center O going to the point P, it's going to perfectly split these two angles in half. And our symbol for this is very similar to the last symbol, except we draw a line down the middle, and then we draw a line across those, just to show that the angles are equal. Okay, theorem 11. The angle in the alternate segment that is formed by a tangent are both equal. So we can see this angle up here is equal to the angle down here. The symbol for that is just a circle with a tangent and then a triangle being drawn at that point, and we just label the two angles that are the same. Theorem 12. If a secant meeting the circle at A and B and a tangent meeting the circle at T are drawn from an external point P, then the square of this value PT here, so PT squared, is equal to PA times PB. Our symbol for this is a circle with a line coming out to a certain point, and then we draw a tangent from that point. And then lastly, we've got theorem 13, which is that if two secants intersect outside the circle, then the product of one internal secant segment and its external length is equal to the product of the other secant lengths. This theorem is known as the secant-secant theorem. So basically it's saying PB times PA is equal to PD times PC. Now, symbol for that is just a triangle with two secants coming out of it. So as opposed to this symbol up here and this symbol here, which are both tangents, this one is now two secants. Okay, so example 32, asked to find the value of A. Some of the more astute of you will probably recognize immediately that this is going to be a Pythag triangle. So we have this line here coming out to the tangent, so that has to be 90 degrees. So we have that so because it's a 90-degree triangle, we can see that 5 squared plus 12 squared will equal 8 squared, which means 169 equals A squared. So A is equal to 13. Okay, and our last example for today, use the diagram to prove theorem 9. That is to say, two tangents drawn from an external point to a circle are congruent. So we're wanting to prove here that UP is congruent to PT. So this is a congruence problem. The first thing that we want to do is make some triangles because we know how to prove triangles are congruent. So looking at this, we can take out radii from O to U and O to T. And because we're given in the question that these are tangents, we know that OUP is equal to OTP is equal to 90 degrees. So that's using our tangent rule. But this is not a triangle, this is a quadrilateral. So what we also want to do is take a line from O all the way up to P, so we now have two triangles. So consider the triangle OUP and the triangle OTP. We want to show that these are congruent. Well, OP is shared. OU is congruent to OT because they're both radii. And then we have that angle OUP is equal to angle OTP is equal to 90 degrees. So that's what we discovered up here. So if they have a right angle and they have one side and they have a hypotenuse, we know that they are congruent by RHS. Therefore, triangle OUP is congruent to triangle OTP by RHS. So if they're congruent, we then know that UP has to be congruent to PT. Well, that's what we were trying to prove. So we have that two tangents drawn from an external point to a circle have to be congruent because of the triangles that we can create by leading lines from the center to the point of tangency. That's all for this video. Thank you very much.